Hi, everyone, and welcome back for another edition of our NACE Calgary webinar series. I'm your host, Brett Johnson, Program Chair for NACE Calgary. So spring has officially arrived this week in Calgary, and well, what we were graced with was more snow. So it's our annual reminder that here in Calgary, that just because the calendar says it's spring and that patios were open last week, it doesn't mean we're done with the snow. So today's webinar features Daniel Fingas from Corrosion Service. Daniel graduated from the University of Toronto with a bachelor's in engineering science and a master's in electrical engineering. Since joining the corrosion industry in 2010, Daniel's work has been focused on cathodic protection, corrosion control, and corrosion investigation. He's also an NACE certified cathodic protection specialist and a professional engineer. Daniel, we're thrilled to have you join us here today.
Good afternoon.
Awesome. So Daniel, what are you going to talk to us about today?
My presentation is on integrity assessments for buried facility pipe. So basically we're looking at how do you assess the integrity of your stations, of your facilities. And I'm also going to dig a little bit into what is SIPs and what do those measurements that we take out in the field actually mean.
That's awesome. Well, I'm looking forward to it. So before we jump into that, I'd like to highlight our annual sponsors. Their continued contributions allow us to be able to provide this webinar series to our membership at no charge. So today I'd like to highlight one of our gold sponsors, Champion X. So Champion X is proud to be a gold level sponsor of NACE and an active contributor of NACE seminars, technical groups, and events. Their purpose is improving lives. Formerly Nalco Champion Upstream and Alpergy, together their combined expertise is what differentiates them as an oil field equipment, chemical, and automation technology company. And of course, to all our other annual sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and to the next generation of engineers. To each one of our sponsors, we thank you for your continued support. So to see a recording from this webinar and all our other past webinars, be sure to check out our website at nacecalgary.ca, and you can find the YouTube link there to go to our channel. So Daniel will be giving his presentation live. Be sure to stick around after the presentation as we'll move into a live Q&A session. Please submit your questions to Daniel in your Zoom client by clicking the Q&A buttons on the screen. If you're joining us from YouTube Live, please enter your questions in the comments and I'll be sure to ask them. So without further ado, Daniel, I turn it over to you.
So thank you everyone for joining for today's presentation, and thank you to NACE Calgary for hosting this presentation series. As I said earlier, my presentation is going to be on integrity assessments for buried facility pipe. And this presentation is based in part on a 2018 Northern Area Western Conference presentation, was given in Vancouver. And the reason I'm able to share some of this data and some of this photos is from the support of the client that we got at that time. So thank you very much to TC Energy. Now the purpose of this program is to gain some of the confidence that we have on integrity assessments of cross-country pipelines on facility piping as well. Some of the normal techniques that we use for integrity assessment are difficult or impossible to apply in facilities. That doesn't mean you can't do anything. And historically, there was quite a lot of work done in terms of maintaining the CP systems carefully, taking annual measurements. So that gives you a lot of confidence in terms of your general integrity. But digging in is something that you do with a more formal process. So looking at an ECDA, looking at inline inspection, you're looking at hard data and you're able to draw a conclusion about the condition of your piping through those extra steps, rather than just taking your CP data and saying in an ad hoc fashion, yeah, everything looks good. So some of the limitations or challenges that we face in a facility environment are things like really congested piping. You can see in these pictures, now you got a lot of risers, you've got a lot going on, piping crossing each other, you've got varying pipe geometry, diameters, you've got electrical grounding, you've got a lot of appurtenances, buildings, fences, and then you've got operational constraints. You may not be able to take this station out of service without causing a lot of grief to your system and to your customers. So the three available assessment techniques that people typically look to would be a hydro test, an inline inspection, and then an ECDA for the external corrosion. And the hydro test is basically difficult from an operational perspective, and it's also very disruptive in terms of cutting lines, and then drying the lines is also going to be problematic. So you may introduce corrosion problems by trying to assess using a hydro test. It's really not feasible. The inline inspection, cut and tether, that's an option, and it's certainly an option that the client was very interested in exploring, but at the time that this program kicked off and their requirement to do this program became, by the time the program was needed, the cut and tether tools weren't in a position to satisfy the requirements. So hopefully in the future that technology improves, but at this point, they don't have cut and tether tools that are going to be economical and not just too disruptive operationally. So that sort of leaves the ECDA type approach, and that's the approach that was selected. It does have challenges with grounding, it has challenges with congested piping, but they're less fundamental issues in terms of being able to actually do them. So we'll look at what those challenges are in the coming slides. Now the ECDA is described in NACE SP 0502. It's a 4-step process. Many of you would be familiar with it. The pre-assessment is going to be a little different than on cross-country pipelines. Fundamentally, it's the same process, but there tend to be a lot more changes in a facility environment than there are on cross-country pipelines. So you may have multiple revisions of drawings, multiple iterations of compressor station A, then you add B, then you add C, then you take A out of service, and then you add aftercoolers. There are a lot of things that can happen, and all of those can involve piping changes, or you add new lines and you're changing the configuration of the piping. So capturing that takes extra effort, shall we say. The indirect inspection, we'll talk about in the coming slides, some of the challenges. The direct examinations, they eliminate some of the challenges that you would normally experience with landowners and land access, but they introduce other challenges related to the environment. So you're going to be doing mostly or exclusively hydrovac excavations. You're going to be near buildings and have to worry about the integrity of the not having much space when you're doing the digs. And then the post-assessment process is going to be similar, except it'll be based on the rest of the results from the other 3 steps. Now, there were 2 small stations that were selected as a pilot program. And this is looking back 7 years now, but as I mentioned, the data that we have and the photos have been approved for public consumption. So that's really helpful to be able to share the findings. And it turns out that the pilots program was selected very well. So some of the challenges that we were looking at were represented in, for example, this slide here. So you can see we've got congested piping, we've got valves, there's isolation in these areas. Yes, it's a relatively small station, but it has those characteristics. It's got electrically continuous grounding as well. Now, as a bit of background, when we were approached to do this, it was about a year or 2 after we were approached by a client to do compressor station surveys, SIPs and DCVG surveys in a compressor station. And at that point, we told the client, you're not going to get any useful data, but we can do it if you want. And they said, yeah, we know we're not going to get useful data, but we want to do it anyway. And we said, well, okay, well, we'll do it for you, but you're not going to get any useful data. And we did it, and they didn't get any useful data. So then when we were approached again and said, hey, there aren't really other good options, what are we going to do? And we said, okay, well, let's give it our best shot, and we'll look into leveraging our experience with stations. We've done a few surveys on the risers coming into stations. We know that the gradients are crazy. So we had to plan really carefully. And they also wanted a pretty quick turnaround. They basically wanted to dig right after doing the survey. So that was a bit of a challenge as well. So here are some of the challenges that it's really different than doing a cross-country survey. Cross-country survey, you've got issues with land access. You may have rivers and swamps and crossing fields with crops and that sort of thing. Here you don't have any of those challenges, but you have a very complex environment. You may have ground contact issues if there's a lot of gravel. Some stations have a pretty thick layer of gravel. in some spots in the stations. And you can see here, this is not so unusual. There are a lot of risers. The risers represent valves or blowdowns. And these supports, for example, is this support contributing to a coding defect indication? You really have to find that out when you're on site because you can't tell after the fact. So skill of the technicians is absolutely critical to the success of this type of survey. And it's critical that the technicians maintain a good awareness of the surroundings. So they need to know what's going on. They need to recognize if there are problems or potential problems, and then they have to act on them right away. The survey is in a small station like this, it might take a day. So you need to be able to respond quickly, and then you probably, well, you certainly don't want to come back because remobilizing is going to increase your costs dramatically. But the office staff also need an awareness of the surroundings. So the tech not only has to pay attention themselves, they need to be able to convey that information back to the office. And then the office needs to provide prompt feedback because they're going to have a different visibility on the data, and they're going to need to be able to ask for more information, for clarification. The best technician can't see that as you have different gradients interacting. So it's really a team project, and both teams need to be on their game. Now this one, we were on site and we were asked before we left to identify dig spots. Now that's not the normal process, but preliminary dig spots, this represents a preliminary dig spot, for example. So we were flagging things before we left, and that's the kind of turnaround that we were looking at during that pilot phase. One critical step is tool selection, and I would recommend using the integrated SIPS DCVG survey. So the SIPS is for protection level, we'll talk about that shortly. And there are different tools that you can use for coding quality surveys. And the DCVG survey is advantageous because it allows you to size the coding defects. And it's the integrated survey technique allows you to size the defects based on the local gradient shift. So some of the techniques will look at sort of representative shifts remotely or the signal strength or something like that. But in a station, those things are going to be really hard to characterize. You really need a local gradient. Let's talk now. We're going to pivot a little bit. I want to give you some background on these techniques, the SIPS and the voltage gradient surveys. So the relevant NACE standards are TN0109, SPO502. For the ACVG and the DCVG, I've listed the ECDA standard here, but it's actually the old version because what it did is it gave some guidance for how you would classify indications. And part of the ECDA, part of your job as the ECDA practitioner is to classify indications. And the old standard gave some guidance. The new standard pulled it out when the survey procedures got pulled out. So there's a little bit of a gap there, but you can refer to those documents. Now, in terms of the voltage gradient test itself, this is basically the setup. You attach to your pipe and you apply a DC or AC voltage source, and then you discharge current from a temporary or permanent ground bed. And when you do that, you're going to have current which is discharged from the ground bed and picked up on the pipe. And this is basically what I'm trying to represent over here. So this black mark is meant to represent a coding defect on my pipeline. And the blue rings and lines represent current and a voltage gradient in the soil. So around a coding defect, you have a concentration of current. That concentration of current passing through a resistive medium soil generates a voltage. And that voltage is what we're looking for when we do a survey. So we walk above the pipeline, and basically what we do is we measure the voltage right above the pipeline to a location offset, say 3 meters away. And that voltage difference is picking up the voltage gradient associated with that coding defect. So some of the considerations that are relevant to a station is going to be the spacing. In a station, you've got a lot of piping tight together. So you need to probably pull back on the spacing. And that's going to lower your sensitivity a little bit. Instead of 3 meters, you'll see more gradient. Maybe you can only do 1 or 2 meters. In terms of defect sizing, the DCVG really has the advantage in that area. We'd recommend using that. And the other thing you need to do is have an orderly survey. You need to know exactly where those gradients are being measured, because if you don't know where they're being measured, then you're going to end up with garbage data because you just can't interpret it. The gradients are very complicated in some of these big stations. Now let's look at CIPS. The Close Interval Potential Survey, or CIS, is referred to or described in NACE standards SP 0207, TN 0497, and then the criteria in SP 0169. And SP 0169 is the criteria like the -850 millivolt CSE, polarized potential criterion, and the 100 millivolt criterion. And those are the things that we use for assessing protection levels. So the CIPS is pretty much a mandatory part of any ECDA, and it's going to be really important to recognize where you have the possibility of active corrosion on your pipelines. Now, conducting a CIPS, basically it's like doing test post measurements, except instead of just setting up your reference electrode right beside the test post, you're walking along the pipeline and taking periodic measurements at some spacing along the pipeline. So here's your voltmeter. You've got a short lead down to your reference electrode and then a long trailing wire back. And this is completing your electrical circuit for your voltage measurement. Now, a couple of important considerations for a CIPS is the soil IR drop. So if your rectifiers are on, then you're going to have current for sure going, well, hopefully you have current going to all your coating defects. And that we call the soil IR drop. And if that's present, then instead of measuring the true polarized potential, you're measuring an on potential with an unknown error, effectively an error. So we want to eliminate that. And the normal way to do it is to interrupt the rectifiers. And we call that an instant off potential. It has limitations, but it's pretty normal technique and it's a very powerful technique. Now, another thing in a facility environment, the connection point could be pretty important. So if there is isolation in the station, you got to make sure that you're surveying while you're connected to the correct side of the isolator. And it may sound simple, but it can actually be pretty difficult to get this right. And you want to get it right. So that's something to consider. The spacing of the survey is important in a facility environment where you have a lot going on and a lot of steep gradients. Probably a meter is going to be a reasonable spacing. And then the nearby features in a facility environment. You need to be paying attention to things like building foundations, to the electrical grounding, to fences, anything that's around that could influence your measurements. So that doesn't mean that you throw out measurements, but what it means is you have to understand how those features are interacting with your measurements. And that's what I'm going to discuss a little bit in the next few slides. So when we take that measurement, what are we actually measuring? So some of you may be familiar with this diagram or one like it. This is from CP3, and it's in the CIPS section of that course. And this is what I'm calling the 120-degree rule of thumb. So here I have my voltmeter, here's my reference electrode, and imagine shining a flashlight, a wide beam flashlight down from the reference electrode, 120 degrees, and then it shines on the pipeline. So this understanding of what the reference electrode is seeing is actually only valid for bare pipe. So most of us are not dealing with bare pipe on a regular basis. So this nice rule of thumb may not be, or likely is not applicable to your regular surveys. Okay, so what can we do? Well, elsewhere in CP3, there is this representation of a mixed potentials approach. So here we have a reference electrode, the voltmeter, and saying the voltage you measure is related to all these different parameters. It's related to the voltage of holiday 1, the voltage, that is the polarized potential of holiday 2, and the resistances between all those things. And this is from an AGA report. Maybe you could find it under PRCI. The reference is down here now. It's saying E core is this plus the difference between those two divided by R prime, which you can find the definition. And then this relationship based on all the resistances of all of these different features. And I don't know about you guys, but for me, it's really difficult to visualize this and say, well, what is the contribution of such and such feature in my potential measurement? And is there a better way? So I want to introduce to you a better way. Now, as background to the better way is this diagram. Gummo prepared it in 1993. Pipeline steel is represented here. The coding is this dark hashing. And then this is the voltage gradient. So these are those blue lines that I showed sort of schematically in one of the previous slides. And this is a 1 centimeter diameter holiday. And what it's showing is how far away do you have to go to get to remote Earth? Or how much of my driving voltage is consumed, how far away from my holiday? So this is interesting because it's a 1 centimeter diameter holiday. And at a distance of 1 centimeter, I've already used up 50% of my driving voltage. If I go to 10 centimeters, 10 diameters, I'm at 95% of the way. So if my driving voltage is 100 millivolts, I've used up 95 millivolts in the first 10 centimeters on this little holiday. Now, what does that mean? It means that remote Earth comes really quickly for small defects. And that's sort of important to understanding what the SIPS is, and we'll look at that on the next slide. But it also impacts our ability to detect coding defects. So the driving voltage is going to impact our ability to detect. So will the defect size. A bigger holiday is going to be easier to detect. The voltmeter precision and sensitivity. So do you measure to the millivolt or to the 10th of the millivolt or what? Your ability to get good ground contact. So if your reference electrode being in contact with the soil is causing a bunch of noise, a few millivolts of noise, that could easily mask a really small holiday. And then there may be some noise as well from stray current. So that sort of depends on the scenario. All right, now this is a bit of a busy slide, and I'm going to spend some time on it because I think this is really critical to understanding SIPS, which is really the result of gradients. So let's start down here. Here's my pipeline that I'm imagining. I've got a coding defect here. So this is the cathodic gradient. I've got current going towards my coding defect. Over here is an anode connected to my pipeline. And at this location, it's an anodic gradient. The current is discharging from the pipeline. So it looks similar, but it's going to be a little bit broader because the anode is geometrically bigger. So that 10 diameters is going to be a larger distance. And it's in the opposite direction. Okay, so what does that look like if I'm doing SIPS? So here's my voltage. I've got negative voltage up. That's just the convention I'm used to. And then this is the chainage going horizontally along the pipe. So here I can imagine this is what I'm measuring, my voltage, pipe to soil potential. Let's say this is just an on profile with a direct connected mag on my pipeline. I come close to a coding defect, I have this sort of classic dip. If you've dealt with SIPS data, I'm sure you've seen that kind of dip. And then I come back to a flat section, and then I reach my anode and I peak up. And then I come back down and go to remote Earth. Effectively, this is remote Earth. This is the voltage at remote Earth, and whether I'm measuring here above the pipeline, on the soil, I can't measure at the pipeline. But if I was here or if I go 10 meters away, it doesn't really change because there's no concentration of current at that location. Now, these are not actually the true potentials. The anode, of course, I never measure the anode potential minus 1750, minus 1700 may be polarized, but I'm measuring, let's say, minus 1500. So the difference between this minus 1500 and the minus 1700 is because I'm not measuring on the surface of the metal, I'm measuring on the surface of the ground. So there's some residual IR, soil IR drop there because I'm not actually touching the metal. And from the previous slide, I'd have to be really, really close to effectively eliminate that. So being 10 centimeters away could already introduce a whole lot of soil IR drop. So here, this is the true anode potential. And the corollary is that the true cathode potential is not my dip here. It's going to be below this dip. So it's more electropositive than what I actually measure because there's current in the soil. Okay, so the question I want to ask now is, if I take this measurement here, is this a measurement of the anode or of the cathode, of my coding defect or my anode? And the answer, of course, is yes, it is. It's actually both. So let's imagine a measurement, and we'll see why I say that. And this is basically the lesson that I want you to take away from this presentation. So here's my pipeline. I've connected my test lead to the pipeline through a test host, of course. I've got my voltmeter here, and I've got my reference electrode planted right at this location. Now, my voltmeter is a 2-terminal device. So you hold it up, you've got a red lead and a black lead, and I can connect them to something. I have to connect them to 2 things. So one of them goes to my reference electrode, and that's my stable point that I compare against. And it's not meant to introduce some strange voltage. It's a stable thing to measure against. So let's say there's no voltage introduced by this point up to the point that I go into the soil. And there's no voltage drop along the lead either. So there's no voltage drop here, and I'm sort of setting at a stable reference point. Now what I need to do is apply Kirchhoff's voltage law and go around my circuit and take this electrical circuit and add up the voltages. So here I come in my test lead. The measurement current is very small, so there's effectively no voltage drop on the test lead, which isn't used for current carrying. And then let's imagine, just for simplicity, that there's no voltage along the pipeline either. That's fairly normal and would typically be true in a station. So I've gotten to this point. I've got a metallic connection between this point and my reference electrode in the soil. Now, if I pass through my coating defect, then I'm representing the metal to soil potential. So that's what I want to measure. That's my polarized potential. So that's what I'm looking to measure. Good. I've got it included in my circuit. And then if I pass from here, the soil, over to my reference electrode, then I have to pass through this voltage gradient here. So I'm climbing up out of the voltage gradient and arriving back here. So effectively, I'm measuring between this true cathode potential over to my reference electrode here. So I have to climb up out. And I climb up not only the part that I measured from grade, but I climb up the rest of the voltage gradient as well. Okay, so that's my cathode potential. Now, what about the anode potential? Well, I can do the same process. So I follow the wire, it's short, so very little voltage drop, although you could account for it if you felt strongly about it. And then we come again to the junction between the metal and the backfill in this case. So that has some potential. Now, instead of climbing up, I'm climbing down, and I climb down through my voltage gradient and I come back here. So what voltage am I measuring? I'm measuring the voltage of both the cathode and the anode at the same time. And the difference is the voltage gradients in the soil. So I'm seeing the same voltage, and it's just the difference is those voltage gradients. All right, so let's pivot back to my facility environment. And if you've got some questions about that, we can certainly address it a bit later. And I want to keep us moving so that we will have time to go through some questions later. So here's some data that we collected in one of those small stations. Let me explain the graph. On my vertical axis on this side, I've got the potential. That's my SIPs, and it corresponds to these 3 lines here. The orange, which is the on potential, the blue is the instant off potential, and the yellow is the criterion, the -850 criterion. I've got chainage across the horizontal axis. You can see it's a fairly short line. That's going to be typical in a station. And data organization is going to be really important in a station. On the other axis, I have the gradient in millivolts, and the green line is going to be measured on one side of my pipe. And then every so often, as required, we have an aqua point, which is the voltage gradient measured on the other side of the point. So in this location, we see I'm fully protected with this blue line being above -850. And then as I assess my gradient, here you can see it's fairly flat. At this point, we have a little bit of a peak, and this represents a coating defect, typically represents a coating defect on my pipeline. And then I continue, and here's a little bigger coating defect on my pipeline, and maybe some extension of it here. Okay, so it appears that I've got a couple coating defects in my pipeline, but hold on. I've got my other side, my opposite lateral gradients. So what's happening is this means here I've got current, which is in the direction towards my pipe. So I'm seeing current coming towards my pipe, but on the other side, it has the opposite sign. So my 0 is right here. So it's passing with the other polarity, which means the gradient, instead of coming to my pipe, is passing my pipe. And the same thing is happening here. So it appears then that instead of being a coating defect on my pipe, it was actually associated with the building that was right next to this location, and specifically the electrical grounding. So there were ground rods at these two locations. So it was very satisfying to be able to go in the field and say, okay, there are actually ground rods here, and therefore I'm confident that these two don't represent, at least not by themselves, do they represent coating defects on my pipeline. And I'm also happy to see that my protection levels indicate I'm fully protected. All right, here's another example of some results. So the configuration here is a north-south. This is basically the main pipeline in the station, and it's got a whole bunch of T's to different laterals. So it has a valve at this location and then a bunch of T's to laterals. And these laterals have their own valves, so you can shut down those lines independently. And you can see a few things to observe. The blue line, again, protection levels. I'm fully protected in this area. I do have a coating defect here. So this is what a real coating defect would look like. This is my 0. And you can see that both the aqua and the green points are on the same side. That's basically indicating that I've got a coating defect there, and it's showing up. Here's my sizing information. That's a 13.8% IR. That's how we size DCVG indications. Now let's look at this one here. This is the point I'm interested in. It looks like a coating defect from one side, but on the other side, it looks like a crossing gradient. So we're going to look at the pictures in the next slide, but you can see that the magnitude of the crossing gradient is a lot smaller than is the magnitude of this gradient. Okay, so this is the basic configuration once they dug it up. They've got our pipe here, and then the tee off, and there's this valve. So that cross gradient measurement that I mentioned is going to be very sensitive to the reference electrode placement. So was my reference electrode lined up with the valve? Was it on this side of the valve? Was it past the valve? So all of those would result in different cross gradients in my measurement. So this is why I told you earlier, it's really important to have an orderly survey so that you know in the office exactly what was done in the field. All right, now there was an issue of concern. Now you can see that this valve is poorly coated. Okay, that basically confirms that we had the cross gradient we talked about. However, there was a small coating defect on the T. Now we didn't see the coating defect on the T, at least I couldn't point it out in the data. So what's going on? Well, we can have what's called shielding when we normally talk about cathodic protection. Effectively, this valve is partially shielding this, and that represents itself in our DCVG data as a term I'll call masking. So you can't see this little tiny coating defect because you've got that big coating defect. Now, what's the significance of that? Well, I'm fully protected, so I guess I'm not really concerned. And in fact, when you've got a valve that's fully protected, you got good confidence. You move a little bit away, you're going to be fully protected on the coating defect as well. However, if you're not fully protected, then that introduces uncertainty. So the valve may not be fully protected, but you don't really necessarily care about the valve is slowly corroding. It's very thick. It's got effectively a very, very long life. However, if you had a coating defect nearby and you're unprotected, that could be problematic. So that's going to come down to an interpretation thing. You need to understand very well what the data is telling you. All right, so this is a diagram just illustrating what that scenario we talked about. We've got a small holiday. Let's say it's a 15% IR holiday. Then we've got a poorly coated valve here. So here's my main pipe, my T to my lateral. And this is what the data might look like. If I only had my small holiday, then I'm going to have a coating indication like this. It's a little peak with my aqua on the same side. If I've just got that big holiday on the poorly coated valve, it's going to be a much bigger peak and I'll have a cross gradient there. Now, if they're both there, you can see that there's actually very little difference between the two cases. So I add both holidays and it's basically indistinguishable. So then you need to say, well, what is the significance and treat it appropriately. I want to speak just briefly about the complexities of the dig program. And you can see just by the pictures of the digs, you've got a big hole. You're going, in some cases, fairly deep. There are a lot of moving parts here. You may be close to buildings. You may have cables crossing. You may have grounding that you're unearthing. All of these things make some of the dig issues pretty difficult. You may have a long section that you're interested in, depending on what your survey's found. And here's a picture of the guys doing a survey in one of those stations. Now here, I just want to draw your attention to this data here. This was in that first station that we did. And we had a nice big coding defect. Well, nice big. Very satisfying to find it in the field, although of course, that's not what anybody wants to have on their piping. So kind of competing priorities in terms of who wants to see what. But we had this coding defect. It was fully protected, so we didn't expect to see any corrosion. It wasn't at a valve, so we were really interested to see what it looked like. Dug it up, and yeah, it was confirmed. There was quite significant coating damage in this area here. And in conclusion, I'd say that the coating defects have correlated pretty well with the DCVG indications. So overall, the program has allowed the facilities to gain a lot of confidence, people to gain a lot of confidence in terms of, do we have a problem in our facilities? Can we effectively isolate it with these techniques? And there were a lot of digs that went into gaining that confidence. Now, there definitely are challenges around valves and risers. They complicate things and they need to be accounted for carefully. And you won't have the same degree of confidence sometimes that you would have on a simple survey on a cross-country pipeline. Nevertheless, you still get a pretty good understanding of what's going on. Disbonded coatings are still problematic, and because you have so many different types of coatings and there may not be a lot of certainty on your coatings, that can be an issue. But overall, the program has been effective at minimizing the impacts to facilities by identifying priority dig locations and also proving out the integrity of the facilities, which is the overall objective. So with that, I'd like to thank you for your time. My contact information is here. If we don't cover your question or if you'd like to discuss further, please get in touch with me. And with that, I'll turn it back to Brett and see whether we can have some Q&A time.
Awesome. Thank you, Daniel. That was a fantastic presentation. Lots of good insight on that. We've already got a few questions rolling in. So if you've got a question, please submit it through your Zoom client or through the YouTube Live and should ask it. So maybe to get the ball rolling, what are some of the lessons that you've learned since you started this whole program?
Yeah, that's a question I think that it should be relevant to anyone who's doing a program over a period of time, is how are we improving all the time? And one of the things that we learned is we don't really care about our big poorly coated valves. Now, if I went into a random station, I could probably point to a valve without doing a survey and tell you that it's poorly coated and that you don't have any integrity issues on it. So that forced us to change up the normal prioritization that you do for ECDA. And ECDA allows you to do it. It's your job basically to prioritize things properly. And valves get downgraded because that's not what you're most interested in. You want to assess the conditions on the piping, not necessarily the conditions on a valve. Now, if you do have to dig up a valve, sometimes it makes sense, and then you got to respond accordingly.
Awesome. It sounds like a lot of good learnings out of that. Yeah. So when you're talking about DCVG indication sizing, so are you able to resolve these at the absolute level or kind of a relative level?
The percent IR is not so much an absolute level. It's not that you can't do the math and come up with an absolute number. And I've seen that done sometimes, but there's a great deal of uncertainty, and if you've got a 48-inch pipe and you take a measurement at grade, is the coating defect on the top or the bottom or the side? You have no idea. Well, you may be able to differentiate between the side and the top or bottom, but that makes a big difference to the depth, and the depth makes a big difference to the sizing. So it's an estimate, and it's a useful comparative estimate, but it's not an absolute sizing.
Awesome. Yeah. Fair enough. I would imagine it can be very tricky to lots of variables to be able to understand what exactly we're looking at and estimate how critical potentially some of these features are on that, and how bad you may need to create one of those massive dig sites, as expensive dig sites to go repair. Like you said, oh, one of the things I noticed when you're looking at the photo, like, yeah, it's great to find an area where you've got a coating holiday, but you know, in some cases, it feels like if you're spending that kind of money and it's only like a little bit of corrosion, you know, was it, did you really prevent it, or was it really worth it?
It's the CPU that's preventing it, right? So
Right.
the point of the digs is to confirm your findings. It's to confirm that your process is valid, basically. And I would say, yeah, you should be happy if it matches your expectations. And that was certainly, you know, in the early stages, you're doing that kind of dig to validate the process. Once you gain the confidence in the process, you probably aren't interested in doing that kind of dig. Yeah, we're fully protected. Looking at historical data, we've been like this for a long time. There's no reason to be doing a lot of digs. And that's the direction the client is going.
No, that's perfect. No, thanks for that insight on there. So maybe a bit of a clarification. So, you know, within your example, you kind of showed a lot of congestion on there. Did you find any presence of environmental membranes? And, you know, what was the impact on the planning and data quality based off of that?
These ones were done on gas piping, so we didn't have a lot of membranes to deal with. But absolutely, if you've got membranes, then it's going to either change or nullify your ability to do the surveys at all, or at minimum, you're going to have to take that into consideration.
Fair enough. So what about can you talk about some of the challenges, say, for example, when your entire site is flooded with CP? So maybe, yeah, just lots of current from either impressed current system or something like that. How would that affect the results? Would you still be able to get the accuracy that you're looking for?
Most of the sites, I think, that we dealt with are in a flood type system. It's really difficult to maintain effective isolation. And some clients do it, and that's great, more power to them. But it's easy to short between your pipeline and ground by accident over time. And what we found is, in general, we're shorted to ground on these larger facilities. Now, what that means is you may need distributed ground beds all over, especially if you've got older pipelines and their coating is in rough shape, then it really adds complexity to your survey, and the surveys, and then it layers on the difficulty for the technicians in terms of they're turning off ground beds, they're disconnecting things, they're connecting things, because you need enough voltage gradient shift to be able to take a measurement, but you want to eliminate as much local gradient as possible so that you're not just seeing an anode gradient, you're seeing something associated with your pipeline. So it's certainly doable, but it's going to add complexity, and yeah, that's part of the fun, I would say.
Fair enough. Well, what if you add a bunch of sacrificial anodes within there as well? What would that do? Would that add complexity as well?
Yes, of course it adds complexity. But it depends on a lot of things. So if you've got sacrificial anodes, then are they depleted or not? If they're depleted, then they basically act as a coating defect because they have a steel core. So if you've got sacrificial anodes plus an impressed current system, perhaps they haven't depleted as much or as rapidly, depending how old they are, of course. And then you need to try and account for that. And sometimes you can. Sometimes you'll label this, well, we know that there's an anode at this location that shows up on the drawing, but then you need to try and assess the risk and say, well, do I think that my measured potential is representative enough of the off potential that I can trust it? Or do I think we need to do something more in order to validate that assumption. So yeah, it certainly makes it more interesting.
So when you're surveying surveying your facility environments, have you ever encountered issues with effects from the DC couplers or some PCRs, and how have you been able to deal with them?
That's a great question. We haven't dealt with it too much on facility piping, but we've certainly encountered it on cross-country piping. And the way you deal with it would be somewhat similar. So if you can disconnect it, great, do it. If you can't disconnect it, then what the PCRs or the SSDs are doing is they act as a voltage source, which attenuates over time. It may attenuate very quickly in a station environment, so that you may actually be okay with just having a little longer off cycle and then accounting for it that way, because there's a lot of grounding and there's typically a lot of bare metal on your piping as well. That may not be true, and in which case you start to rely on coupons or other techniques to try and characterize how big that residual soil IR drop is. Because again, it's as if you have this rectifier still connected. That's what an SSD acts like in the short term.
Crazy. Awesome. Thanks for that. So I'm curious about, what was kind of your decision criteria for how you decided that you wanted to dig up a site? Do you have thresholds that you set? Do you use something like, percent IR drop or ACVG or something else? How do you decide you're going to dig up this area, that you want to dig up there?
Mm-hmm. Well, fortunately, in this case, we're partnering with a client on this, and we had some input and we made recommendations, but they were making that decision. And the reason that they took that decision on is they wanted to cover off some other concerns as well. So when we were making recommendations, we were considering things like the external coding type, because we want to see some variability there. We want to understand what's going on. We were considering certainly the SIPs. That's the primary factor that's telling you, yes, you need to dig this up because there might actually be a corrosion risk. If you've got a big coding defect and you're fully protected, I have no concerns. It's when you have marginal or you are not fully protected that you really want to consider digging that up. Now, if there's uncertainty in the survey, then maybe that's a reason as well. Now, the client had other considerations. They're looking at things like dead legs. Do we have internal corrosion problems and other issues like that? So there was a lot of communication there. And sometimes you'll be able to swap out a dig for another site and say, this is roughly equivalent. Let's not spend all the extra money because I've got this other structure nearby and it's going to make my dig cost twice as much. So it's a very interactive process. And I think as long as everybody's got their objectives clear, then, you get to decide. And we don't have to follow SPO 502 to a T in this case, because we're generally not under the same regulatory regime that cross-country piping are under. I know in the States you have to follow it to a T on the cross-country piping in certain areas, but here that's not necessary even on cross-country piping. But here, when you're doing a more targeted approach, I think you end up with very similar reliability, and you're actually able to investigate certain locations that maybe you wouldn't be able to afford if you have to dig up a bunch of validation digs or something, once you have confidence in the process.
Huh. No, that's fair. It's tricky because, yeah, I mean, most times, especially if you're doing a survey and as an operator, sometimes you're looking at going, I don't know, is it a risk? Is it not? Should I be doing something about it? So it's kind of trying to understand what are those guidelines that say, yeah, this one's a problem and this one's not a problem. And, I don't know if you could provide some insight of what out of that data really kind of helps you say, yes, let's go to this point here instead of these other points, especially if you've got, say, a facility piping with potentially lots of indications instead of just a couple.
Well, the guidelines really, the SIPs is your key tool. And then the other thing is, if there is uncertainty in the coding data, in your coding quality survey, you want to dig up a representative location. So you want to make sure that you pick a spot that actually has a coding defect, because that will at least give you some information. So sometimes there may be ghost readings or cross gradings that you're not 100% sure about. And so you want to start with the ones you're sure about, and then you can say, well, do I actually think that there might be a problem? And if there is, then you can begin to take further steps. I don't think you want to make a decision right up front. I'm going to dig up these 5 spots that are marginal. Like, okay, well, what can I learn from one spot that's marginal? Maybe there's a ground rod nearby, and that would make this the worst spot. So then we take a look at that location. But you can see that it's very site specific. We had one location with underground entries into a building, and every single one of those entries had a super big drop in the SIPs, and that had to do with the building's foundation. The reinforcing steel and concrete was connected to electrical grounding, which was connected to our pipeline. So the potential of steel and concrete is a lot more electropositive than steel and soil, for example. So there's a potential for galvanic corrosion, but it's really hard to differentiate between a coding defect on our pipeline, would it really be protected, and the rebar, which we don't need to protect at all. So there's a lot of complexity there.
Fair enough. No, thanks for that insight on that. That kind of helps clarify that a little bit for somebody who's never done something like this before. So moving forward, is there any kind of either a data analysis or some kind of signal analysis that you can do ahead of time to understand what kind of signal quality you can get within a facility? Something you would do before you might do a SIPS or look to use another method to identify coding issues?
There aren't that many options, I would say, is one perspective on it. And in terms of the issues you might try and predict ahead of time, it would be ground cover. So if you got a lot of gravel, that could cause you a lot of grief, or at least slow your survey down significantly. If there are a lot of distributed ground beds in the station, then that's indicative. Now, distributed ground beds are installed because somebody saw a problem. So if somebody saw a whole bunch of problems, it means that there is a bunch of coding damage, which is making it difficult to get CP around the station. So then that would be a sign for you to say, okay, I'm going to have some problem getting my signal that I'm trying to measure around my station. And that's another problem actually with trying to use the ACVG, is you're going to be moving that signal source around all the time because it's going to get consumed really quickly. Whereas DCVG, you've got all these permanent rectifiers that can put out a lot of current to existing good grounds.
Awesome. No, that's very insightful. Thanks for that. So we've got time for, let's try for about 3 more questions. I've already got another 10 queued up in the queue. So thanks everybody for sending them out. This has been a great interactive session. So we'll try and get through a couple more that we can. So so what about, in your company experience, have you ever witnessed any kind of significant corrosion on risers at the soil transition? So, and then, if you have, how has this impacted the data evaluation on the buried pipes?
Yeah, that's a really good question. We have sometimes seen issues, especially at the transition, and there can be some variability as to whether that transition is going to be represented in your data at all. So it may make sense to have it assessed a bit separately. Basically, dig down a little bit, take a look at it, because it's accessible, right? You don't even need to do ground disturbance if it's close enough to grade in one of these facilities. So that may be a good option for eliminating that coding damage right at grade and then assessing it. And then once you've got that, then you've pulled that out of your data set. So it's not going to contaminate any other data along the way. So that might be a reasonable approach.
That's very interesting. No, fair enough. Moving on. So when you, so just out of curiosity, so when you're trying to decide to do some kind of follow-up digs or investigative digs, how do you, how much confidence do you have on where exactly this location is? Can you measure it down to say plus or minus a meter, or is it 10 meters, or is it 20 meters? How accurately can you pinpoint where this, where the coating despondents are?
Yeah, that's a good question. We are typically doing survey resolution at 1 meter, and we're pinpointing, if you're 1 meter away from the valve rather than the valve, then we're going to point you to 1 meter away from the valve. And in a facility environment, sometimes with the buildings, you can have problems with your GPS, if you're running the survey right beside the building. But what we found is it's actually better just to reference it based on the risers. So you're doing the survey, if you're being very careful with your chainer, because your GPS might not be functioning properly, then you can have a lot of confidence as to how far away you are from such and such above ground feature, of which there are tons in most stations. So you can basically say exactly where you got to dig.
That's awesome. Would you always want to try and make sure that you survey at least every 1 meter?
I would certainly recommend that. A couple different reasons. One, the voltage gradients change so quickly. Two, if you do have a bad read, then if you lose 1 meter, it's not the end of the world. You don't have to go back out and retake the measurement. Maybe, sometimes you do want to do that. But yeah, 1 meter is probably reasonable. If you're going to 3 meters, then you're going to start missing features.
Fair enough. Is there any advantage to go even tighter than 1 meter?
Possibly, yeah, sometimes we would do that. I don't think you're going to see that much more, but if you want to, yeah, it's going to cost more. That's always important.
Well, of course, you want to make sure you get what you can while the crews are out there and the expense has already been paid.
True.
No, fair enough. So what impact does ambient ground and soil conditions have on performances of either tests, like such as water content or soil resistivity or that kind of thing?
I would say it's generally not an issue as long as you have some moisture in the soil. So if you've got very, very dry conditions, then it's going to impede your ability to take the measurement at grade. But the type of soils that we get in Canada are typically not going to be so dry, except at grade, where it'll interfere with your measurements. But other than that, you're basically able to take what you need to take.
Awesome. So we have time here for one more question as we've just hit 1 o'clock. Actually, we're probably a little bit over, but I'll still got 10 more open questions on here. So within the presentation, Daniel, you showed your contact information at the end of the slide. We'll have this all posted up on our YouTube channel. And so you can be able to find the information, your contact information is there to contact if you'd like to get some more information. So thanks everybody for all the questions, or we haven't been able to get to them all, but last one I'm going to ask, pick one out of here that looks good. So is it advisable to do a thorough underground facility electronic locate and marking prior to starting to do a survey like this? What is the best way to mark out your facility, and like what pre-research do you need to do to be able to execute a project like this?
It certainly helps to mark it out first. And whether the crew that's doing the survey marks it out or you bring in a locating company to do it, in either case, they're going to be using the available drawings to supplement their work in the field. So you need to have a good visibility on where the pipelines are. You need to have a photographic record of what's going on. And generally people are laying these pipelines out in a grid. So it makes sense based on the above ground stuff, what's going on. But when the guys are standing there with their heads down doing the measurements, they need to be following something pretty precisely.
That's fair. That's good to know. All right, so that's our last question. So thank you a ton, Daniel. That was absolutely fantastic. Great presentation, great detail, and awesome Q&A. Thanks for answering all of our questions. Well, I guess not all, but a lot of our questions. And so we really appreciate having you join us today. So, so with that, we're going to close up. Upcoming on our next webinar series, we're going to have Anna Benz from IRIS-NTT. She's going to join us in about a month. So please watch our LinkedIn page and our website when our registration goes live. And so if you yourself are interested in sharing your research or experience, or have an interesting case study that you wish to share to the rest of the Industry Analyst platform, please send me an email at program@nacecalgary.ca. And I'll help work to make this happen. So thanks everybody for joining us again today. Please be safe out there and have a happy Easter. Thanks. Goodbye.
Thank you, Brett. Bye.